Designing highly concurrent multi-protocol, multi-tenant services in Scala. So my coworkers made fun of me for this talk title, but I thought it sounded pretty interesting, and hopefully you all agree. My name is Greg Soltis. For the past 2 years, I've been an engineer at Firebase. I work on our backend as a service product, and it is an example of a highly concurrent multi-protocol, multi-tenant service written in Scala, in case you were wondering where I came up with the talk title. So what are we going to cover? We're going to build, in a couple of steps, a program that does these things. It's going to speak multiple network protocols. It's going to handle a large number of concurrent clients. And it's going to handle many independent applications at the same time. But what's so hard about all of this? The main trick is managing complexity. Any one of these applications or protocols might be simple, but when you mix them all together, running at the same time, things get complicated very quickly. And before we start, I just want to cover a couple of definitions so that we're all on the same page about what we're going to get out of this. The first being network protocol. So I'm intentionally being pretty generic here. I'm not tying this to like a specific level of the OSI stack. This could be UDP versus TCP, or it could just be REST versus long polling over HTTP. The important part is that you have to follow a different code path to send the same message to two different clients. Basically, you have non-reusable code for that same message. Large number of clients. This is an arbitrary number I picked. The main thing I wanted to do, sort of with apologies to the Node crowd, is rule out single-threaded solutions. We're going to handle a large number of clients, and we're going to do it with multi-threading and coordination. And finally, application. This is also maybe a little bit of a weird definition for application, but it's kind of a worst case. In the absolute worst case, we're going to need to serialize access to our application state. In the real world, probably your application can be a little bit more parallel, and that's great. That'll improve performance. But we're going to go through a worst case and see how even with that, we can do it and manage the complexity. All right, round one. We're going to go with a program that handles a single application, a single network protocol, and to start off with, we're going to just require that it's only used by one client at a time. So for instance, maybe we have a static HTML JavaScript page somewhere, or corporate intranet portal or whatever, and we're going to write a web service that's going to add a little bit of dynamic content to it. And since this is a very contrived example here, we're going to feel perfectly justified picking something way overpowered for the job. So we're going to use a library called Nettie. Nettie is an asynchronous event-driven network application framework. And it's written in Java, but we're using Scala, and so we'll have no trouble incorporating it. It's all in the JVM. The abstraction that Nettie gives you is a pipeline. So connections are channels, and each channel has a pipeline of handlers, and handlers respond to events on those channels. Events are things like, here's some data to read, or here's some data to write, or this channel is closed. And actually, these handlers correspond pretty well to the filters that Marius was talking about in the last talk. They can take some input and transform it or decide to respond to it or preempt it or something like that. And these handlers are chained together to provide interesting functionality. Under the hood, Nettie is using all non-blocking I/O calls, and it's mapping channels to a group of single-threaded event loops. So our first Nettie application is going to have two main pieces of configuration. This here is an abbreviated version of just setting up a server. It's going to look a little bit familiar to those of you that have done socket programming before. We're binding to a host and port. And the second line there is telling Nettie that when you get a new channel, use this thing to figure out what the pipeline is going to be for it. And that's the interesting part. So here's our first pipeline. We've got some HTTP parsing to start with. We're parsing from bytes to an HTTP request. We're batching up all of the different parts of the request into a full request, which is kind of an optimization, or not optimization, simplification that I'm doing, just so we don't have to worry about streaming for now. On the outbound side, we're going to expect an HTTP response, and we're going to transform that into bytes to be sent back to the client. So far, these are all handlers that ship with Nettie. You can use them or not, but they provide a bunch for common protocols, so we're going to use these. And then we have the first version of our application. So for our first example here, we're going to make a bespoke, social, local, big data weather application. And we're going to use it to let us know if it's foggy outside the Firebase office and we need to wear a hoodie, or if it's not foggy and we should carry one with us for later. And here's a little snippet from the first version of our app. So we're going to use a Scala object, a singleton that's just wrapping a Boolean value and the isFoggy value. And we're directly dealing with our HTTP request. We're saying, OK, if it's a get, just render a response that includes that Boolean. If it's a post, update the state, and we'll respond with the current state as well. Also, let's talk about threading for a second. We're building this application for a single client. And to start with, we're using a single event loop, which has one underlying thread. So right now, there's no concurrent access. And so our singleton with just a Boolean there is fine. But what happens if you open this up in, I don't know, multiple tabs while you're doing development? What's going to happen? Well, it turns out we're actually still fine in this case. Since we have just a single thread, even though we have 2 clients now, they're still going to be processing in serial. The event loop's going to be handling one at a time. It's one thread. So the good news is we can now use this application on our whole team without having to change anything. So what do we have so far? We're dealing directly with HTTP gets and posts. We're taking input and returning a Boolean. We don't have any concurrency yet, but we are handling multiple clients. And we're constructing a response directly in our application there. So this is all pretty simple, standard stuff. Let's move on. Round 2, we're going to get a bit more complicated. We're going to handle a lot more clients and more protocols. So our application was a hit. And the CEO asked us to roll it out to the whole company. One thread is just not going to cut it anymore. We've got a very big company. Load times are going through the roof, and our 16-core server is still sitting just mostly idle. So we're going to have to figure out how to scale this up. So we're going to add more event loops to do that. This is part of where Nettie helps us, is that when we get a new connection, Nettie assigns that connection to an event loop in a pool of event loops that we give it. So this is great. We'll be able to handle a lot more connections by just sharding them over different event loops. But we've introduced some complexity here. Now we have race conditions in our application. That just singleton with a Boolean is not really going to work anymore. And to make matters more complicated, the marketing department got wind of how popular our application is, and they want some metrics for a blog post. They want to know exactly how many reads and writes have happened at any given time. So what we're going to need to do, and remembering that this is kind of a contrived example, is we're going to need to serialize access to our application, because we need to give them exact counts. And for requests that are updating the state, we want to make sure we're returning the state that it was updated to and not some later state in the application. So we're, for now, going to use a lock just around our application state. We'll get a request coming in. It'll block on the lock for the application. It will do what it needs to do, either just update the read counter and grab the state, or update the write counter and grab the state. This is not ideal, but it's progress, and should be able to handle the traffic. OK, we said we were going to add more protocols in this round as well. The head of product decided that refresh is too slow. He wants live updating weather widgets on the company intranet portal. So we're going to add WebSocket support. This is going to be our first persistent connection. This is not just request response. What we're going to have to do is whenever that state changes, we're going to broadcast out the new value to all of the persistent connections so they can all update their weather widget. To make matters worse, the IT department, their collective motto is never upgrade. They still use IE6. So we're going to have to include some long polling implementation as well, just to kind of add some more complexity to our server code here. And on top of that, the corporate firewall only allows connections on port 443, so we can't cheat and just run all of these on a different port. We're going to have to come up with another technique. So in one respect, we're lucky. All of these protocols start out looking like HTTP, which means we can keep our HTTP parsing in place. And what we're going to do is when we get a new request, we're going to look at it, decide which protocol it corresponds to, and reconfigure the pipeline accordingly. So this is another strength of Nettie, is that the pipeline configuration that we saw earlier is not static. We can, at any time in the course of processing a request, decide to completely reconfigure it. So if we notice that we don't, in fact, have a GET request, what we really have is a WebSocket upgrade request, we just reconfigure the pipeline to deal in WebSocket traffic from then on. And since we're using HTTP for these, we can make the protocol detection a little bit easier on ourselves. We can what I'm going to do actually is just use the extension, the file extension on the end of the URL path. So here's some changes to our application. At the top, we're now using multiple event loops. We're going to modify our pipeline to add this stage that looks at what protocol we're using. And then in that protocol chooser, we're going to modify the pipeline accordingly. So here's just a little snippet of checking for if we have a WebSocket. And if we have an HTTP request, like our first version, we can just pass it along to the original version of our application that we had. All right, so our application has to change a little bit, though. Before, we were dealing directly with HTTP requests, and we were constructing an HTTP response that wrapped a Boolean just directly in our application code. And this is a good example now that we have multiple protocols of where abstraction is important, right? So we have instead this trait here that speaks in the semantics of our application rather than in the semantics of the protocol. Like previously, it was like, here's a get or here's a post. Now it's get state or update the state, or here's a new listener that needs to be notified when the state changes, which is an addition in this round. We've got those persistent connections. Anytime we're updating a state, we're going to need to send to them. So if you'll notice in those two methods, the adding and removing listener, there's a type there that says nothing about what the protocol is. So we're going to implement this trait here in our WebSocket and long polling codes that our application, on the inbound side, we said it doesn't need to know what the protocol is anymore. And similarly, on the outbound side, it shouldn't need to know anything about the network protocol. This will help keep your application code simpler and is a good way to modularize your design. And then just here's an example of our WebSocket handler. It's one of the Nettie handlers handling WebSocket traffic, but it's also implementing this trait. It knows how to say, OK, here's a new state. Let's send it to the connected client. All right, so this is what we've got in round 2. We now have capacity for a large number of clients. We've got those 32 event loops that are all processing asynchronous events from different channels. That's going to scale pretty well. We have a protocol-independent application interface, which is good. We talked about getting the network specifics out of our application definition. And similarly, on the outbound side, we have a protocol-independent way for our application to send messages to a client. And we have a few different protocols now. We've got some that are request response. That's our basic HTTP get and post. And we've got some persistent ones, the WebSocket. And even though actually the long polling isn't quite persistent, it presents itself as persistent to the application. The application doesn't care about the details. It just knows here's a persistent connection. All right, round 3. Things with our app are going very well. So one of the engineers noticed that we could apply the idea, synchronizing Booleans, to a bunch of different problems. The Boston office wants to know if there's currently a baseball game, or the New York City office wants to know if Uber surge pricing is in effect. And the HR department loves the live updating SOMO weather report so much, they want to apply the same idea to their PDF to Word resume converter. Unfortunately, accounting doesn't want to pay for another cluster for each of these applications. And they observe that although the latency is occasionally a little high on the weather app, the cores are still a bit underutilized. It's a very technically savvy accounting department. All right, so we're all experienced engineers, and that means we're all probably a little bit lazy. We're not going to overthink this. We're just going to reuse the application code that we have. We'll just put multiple copies under different URLs. So we're going to need to make it a little bit generic. It's not going to be tied to specifically whether or not it's Foggy and Soma anymore. And the HR department is supplying their resume converter code. We'll just need to wire it in. And because we can kind of see where this is going, we're going to put the mapping from URLs to applications in some sort of external queryable data store so that we don't have to redeploy our cluster every time somebody wants to add a new instance of one of these applications. And here's how it might look. So when we get a request, rather than just speaking to that trait before that was dealing with the state of whether or not it's foggy, we're going to look up the specific instance of our application. And your implementation of this could do something like talking to Zookeeper, talking to Memcache or some database or flat file or whatever. You return an instance of the Boolean sync application. And then your protocol already knows how to deal with that. We just replaced that singleton we were talking to before with the trait for the Boolean sync app. And then that same, the Boolean sync app is again just wrapping the Boolean state. It's wrapping our counters. We still have locks in there. All right, so we've got a generic application trait as a result out of this, which is good as long as your independent applications all kind of have similar-ish behavior. You can include some stuff in your external store to customize them a bit. We've got some app lookup that we can do. So our set of applications that we're running is now defined at runtime rather than when we write the code. And our network protocols talk to a generic app, not a specific app. So they're a bit more reusable now. OK, so that's most of what we set out to do. But we still have another round to go. And I kind of snuck in an extra bullet point here to remind us of what we need to accomplish still. I mentioned back in round 2 that there are some problems that we are going to come back to. And specifically, it's a performance problem. So it has to do with how we are serializing access to the application state. I said we were just going to have a lock, and when a request comes in, it would block on that lock and then do whatever it needs to do. So the problem lies in what is actually blocking on that lock. And the answer is the thread underlying Nettie's event loop. So let's say we have one application that's extremely inefficient. Take the resume converting application as an example, and maybe each conversion takes like 30 seconds to do. If we get a bunch of requests for that particular application, one of them will grab the lock, it'll be in there for 30 seconds, and the others will all be blocked on it, blocking the underlying event loop. And what that means is all of the other requests and responses in the system will be blocked because the event loops that were running them are blocked on that one application. And that's pretty clearly not going to work for a multi-tenant service. One of the challenges in a multi-tenant service is giving each tenant the sort of illusion of isolation, even though they're actually using the same shared resources. So we're going to have to come up with a different way of serializing access. So we're going to use Akka. Akka is an actor framework. It's written in Scala. From akka.io, actors are very lightweight concurrent entities. They process messages asynchronously using an event-driven receive loop. All right, so what does that all mean? The basic idea is that an actor is a behavior function coupled with a mailbox, which is usually a queue of some sort of messages to process. The actor system, which underlies all the different actors, is responsible for successively calling the behavior function with each message in the mailbox. Other actors and external pieces of code can, at any time, add messages to the mailbox to be processed by a particular actor. One of the guarantees that we get from the actor system is that a given actor will only be processing a single message at a time. So it behaves in a single-threaded fashion, although we aren't actually guaranteed that the thread running that actor won't change between messages. We're guaranteed that we'll have one continuous run of a message on a single thread. So for our purposes, we don't really care which thread is running it. We just care that access to our application state is serialized. Remember that the marketing department needs absolutely 100% accurate counts. And we said earlier that an application was going to be a single-threaded state machine. It's kind of a worst case here. So this is going to work for us. We'll just use an actor for each application. So Akka actors form kind of a hierarchical model. You can have child actors belonging to a parent actor. And if your application is kind of decomposable a bit and you can run more pieces in parallel, this is a pretty good way to do it. But again, we're going with the simple worst case. We're just going to use one actor per application. And how is this going to work with Nettie? So the network protocols are still going to be running through the Nettie pipeline, the group of event loops that we have. But instead of blocking on an application, they're just going to append a message to the correct application's mailbox. And we're getting that via our app lookup that we added in round 3. So this is going to let us run a whole bunch of different applications, all multiplexed over a thread pool that is the actor system. OK. Nettie and Akka sound kind of familiar, or similar if you look at their descriptions. So I thought I would just quickly cover some of the differences and similarities between them. The real fact is you don't actually need to use both. Like you could implement this design using just one of them. For instance, with Akka, you could assign each channel an actor, and then you would have serialized access to that channel. And with Nettie, you could actually assign each application to a channel, and then you would have serialized access there. But it gets a little complicated, but definitely doable. They each have their strengths, though. So Nettie is very focused on network performance. It uses direct memory buffers and can be tuned to do 0 copy writes, which is great for performance. And it also comes with a whole bunch of ready-made handlers for doing various network protocols and network-related things like batching and rate limiting and stuff like that. Whereas Akka is a bit more generic. So you can do networking with it, but that's not all that it's made for. Where it really shines is how customizable the concurrency model is. So if you have some piece of your application that can be run in parallel, you can use a bunch of different actors for that. And then some part that needs to be serialized, they can all feed into one actor for that. And you can kind of do this in whatever way makes sense for your particular application. And it's pretty easy to do. It's all just sending messages to different mailboxes. Whereas with Nettie, it's a little bit difficult to go from a stream of events for a channel and then regroup them into a stream of events for an application. It's doable, it's just not quite as simple. Akka gives you that flexibility. So we're going to use both of them and try to use the strong parts from each one. All right, so how is this going to look for our application? Let's go through the simple case of just the HTTP requests. Say we get a GET request for the current state of one of our Boolean sync apps. We're going to use the ask pattern, which is the question mark there, and it returns a future. It's a future like we saw in the last talk. It's either going to be empty or have a value or have failed. And we're going to, that ask is sending a message to the actor. The actor is going to get that message. It's going to say, OK, this is the current state, and send it back, which will complete that future. And that's all running in Akka's thread pool. When the future completes, we'll have just a tiny little bit of glue code to kick it back over to Nettie, which knows how to serialize an HTTP request and send it back to the client. The important part is, though, this entire time, the Nettie pipeline is not blocked. It's not waiting on that response from the actor. In the meantime, it can be processing other messages, which might go to other applications, or even the same one. It's just appending them to the mailbox. So similarly, for a post request, we're going to send a message into the actor and wait for a response. Our message here is going to be a little bit different. It's going to include the state that we're trying to update it to. But in general, it's the same idea. And then the last thing that we really need to handle is our persistent connections, the ones that get broadcasts whenever the state changes. So they still need to be registered with our application so that when the state changes, the application knows who needs to get notified. So we're going to send a message in again. This time, we don't need to use the ask pattern. We're not waiting for a response. This is just kind of a one-way message to the application saying, hey, here's a new listener. And so that message will include that new listener. And you can do that one a couple of ways. You could use an actor for each listener, or just a simple hook to get back to the Nettie pipeline. That part's kind of up to you and what makes sense for your application. And so here are some messages that we might use. Scala helps us out here. If you're doing this, I definitely recommend a sealed trait, just so you can guarantee that your actor is handling all of the messages that you can send it. In addition, the messages should definitely be immutable. Given the actor system is going to be bouncing these around to different threads, we don't want to have to worry about somebody changing one of these things out from under us. So again, this is a nice benefit of using Scala for this problem. But here are our messages that, this is how the things our application can do, right? It can get the state, set the state. We talked about our stats and our broadcast listeners there. And this is what the actor, or a snippet of the actor, looks like. So the receive method is the behavior function for the actor. It gets called with the messages in the mailbox, kind of one at a time. And this little snippet here is how we might implement the get state message. We grab the sender for the message, and we log our read and send the state back to the sender, which is going to complete that future and kick back over to the Nettie pipeline. One thing to notice here is that we don't need any locks anymore. The actor system is guaranteeing that we're only processing one message at a time. And since this actor is wrapping our state, we actually have serialized access to our application state just by virtue of using an actor. All right, so this is our final program here. We've got multiple protocols. They're a mix of request response and subscriptions for broadcasts. We've got support for a large number of clients, and we're not blocking the event loops anymore, so that'll let that scale up nicely. The messages just get appended to the actor mailboxes. And we have support for many different applications running concurrently and independently on the thread pool underlying the actor system. The full amount that you can scale that up really kind of depends on your workload. But I guess the max that you can have running concurrently is the number of threads in your thread pool. We also got some bonus results. These are not really stated goals up front, but turned out to be some pretty nice properties of this design. So we have an extensible interface for new protocols. Right? We can implement that listener, and we've got new broadcast protocols. We have those messages that we send to the application. So as long as the protocol knows how to turn a message into a network message into one of those actor messages, we've got a separate protocol, and the application doesn't need to know anything about it. So along those lines, the protocol agnostic interface for each application is pretty handy for managing complexity and also for being able to test. We no longer need any sort of networking or protocol code in our application logic's test code, which is great. We can just send these messages to this actor and expect the state to look like that. And that way, we don't have any sort of latency or race conditions or anything like that in our test code. And finally, one additional benefit that we got out of all this is we actually have an audit log for our application. So we said we were going to use one top-level actor for each application. Well, the list of messages that it processes, and in that order, corresponds to all of the state changes for our application. So what that means is if or when something goes wrong, rather than looking at a log of HTTP requests that came into your system that probably won't have the broadcasts, it probably won't have WebSocket frames, you can actually be looking at the list of messages that were sent to that actor. And you can, if you want, reconstruct them and just replay them, and you should be able to generate whatever problem you observed. And then once you have that, it's much simpler to debug. All right, and that's about it. So all of this code is up on GitHub. You can check out the 4 different versions and see how it works. I left out the long polling and resume converting portions. I also want to say both Nettie and Akka are extremely powerful and very tunable. I've put up code that just kind of grazes the surface in the interest of keeping things simple. Definitely read the documentation if you are building something to operate at a large scale. And also just the obligatory bit, if you enjoy working on these kinds of problems, Firebase is always hiring. This is more or less how our service works. We've scaled this up to handle thousands of applications at a time, over 1 million concurrent connections. So with some tuning, this can definitely work. Yeah?
So you have a committee application. So do you have a more than one actor system, or just a single one actor system?
So we have just one actor system. You can use multiple depending on your workload, but we are on a given server multiplexing just over one actor system. So we actually another kind of nice property between from all this decoupling is this doesn't actually all have to run on the same server. You could be sending messages to actors on remote servers and just have a bunch of edge servers that are running Nettie pipelines. We have them coupled together, but we have our applications split over different servers. Oh, in the back. Sorry? I'm sorry, persistent connections?
Load balance.
Oh, load balancing. So actually, we looked at using load balancers at one point, and a lot of them were saying things like they'll handle 100,000 concurrent connections, and we're like, all right, but one of our servers kind of already does that. So we've done it at our protocol level. Basically, we have a hash ring, and when you connect, each server can tell the client where the actual server to connect to is. So that's what we're doing for load balancing.
I want to thank Greg from Firebase.